Okay, good afternoon, everyone.
Good afternoon.
Okay, let us humble ourselves for a word of prayer before we start our lesson. In the name of the Father, and of the Son, and of the Holy Spirit. Almighty Father, we thank you for the gift of life. We thank you for today. We thank you that we are gathered today on this platform to share this content of physics as a lesson. As we pray, Lord, may you guide each today. Father, we come before you and we seek for the knowledge, the gifts of the Holy Spirit, that we may be good students and listen to the teacher very well, so that we may excel in our academics. In Jesus' name we have prayed.
Amen. Okay,
In the
thank
name
you
of
so
the Father,
much.
and of the Son, and of the Holy Spirit.
Amen. Thank you so much, and thank you for joining on time. We have 2 hours. Is just very little time, so there is a lot that we're going to share in that little time. So I'll share the screen straight away, and we start with our discussion. Okay, I hope it is the one. So we have some questions that we are going to discuss this afternoon, but in the interest of time, I will not go through all of them. Time will not allow. So I picked some of them for emphasis and for some reasons. However, for those who need solutions to each and every question, after the sharing, I'll share the solutions in our group, in our WhatsApp forum. So you'll find the solutions there. Is it okay? But for now, there are some few questions I've selected so that we can understand them in depth. So the overall set of questions are: one is about waves and light, item 1, because I'm not discussing this one right now, but I have the solutions. I'll go straight away through the one that we are going to discuss in our sessions this afternoon. That is number 3. Number 3, 4, 5, I think 7, 8, 9, and 10. So number 3 is about modern physics and specifically half-life. Yes, so I think we shall have some few representatives to help us in the reading of the questions, as others will be joining us. I'll be asking some questions. It is going to be more of an interaction. So someone read for us the question.
Okay, Diana.
A certain town experienced an atomic bomb blast. Many people were killed in the incident and others survived with severe injuries. The government advised the survivors to relocate to other places of the country because this village was not safe for them. The scientists carried out a scientific investigation using detectors of radiation and found out that the environment was still radioactive as shown in the table below.
Continue the question, the scientists.
The scientists recommended that the environment will be safe for use again when the obtained half-life value is less than 60 days, and they will need about 1 year or 365 days for the environment to be free from radioactive wastes and materials. And the task, as a student of physics, use your knowledge to help the people to know the value of half-life and advise them accordingly.
Okay.
Sensitize the people about the risks associated with the radioactive materials and how they should be handled. Help the people to understand the value of the number of neutrons of a nuclide Y formed when a radioactive substance X of mass number 208 and atomic number 104 decays by emitting 3 alpha particles, 4 beta particles, and gamma rays to form a nuclide Y.
Okay, thank you so much. So the question, it is very obvious that it is under nuclear processes. So in that section, we have the first part, which is atomic models. And atomic models, we have the Rutherford's model, and the other one is Dalton's model of an atom, not so. So that is the first part of nuclear physics. Then the second one is one that deals with the nuclear processes. And under nuclear processes, the one that dominates and very important, there are two, but the most important one is the half-life, and also the other one are specifically the nuclear processes, that is fusion, fission, and some others. So this question requires us now to apply half-life and also to determine whether the community is safe or not. So using the knowledge of half-life. So can someone guide us? What do you think if you are a student and tasked to go about this question, what is going to be your step? Yes.
Fungo, you unmute.
Please go ahead.
Okay. Fungo has failed to unmute. Then Shakira.
Right now, what I think is that I should half-life. I might use a graph or use the method. After finding half-life, then I solve. Yes.
Teacher?
Okay. Yes, please.
Teacher, I think for Roman 1, it's maybe plotting a graph of half-life because the method can't give us a right answer.
Okay.
Then Trevor Albert is okay. Noeline.
Okay, for me, I think for the question part number 1, to help the people know the value of half-life. Yes, they're talking about the graph, but after finding the graph, you have to use that half-life to still split these digits up to a number that is less than 60, because it's what they require, advising them accordingly. Yes.
Okay. That is good.
Then lastly, Jonathan.
Yes, thank you so much. Other people, maybe everyone is right, but we can also use the graph to find half-life, and the graph can solve both solutions. So you don't need to use any method. When you use the graph, use only the graph.
Okay. Okay. So we can have we can plot with our graph. It is going to be what again is what? Yes?
Gerald.
Yes, please.
According to me, I think we're going to draw a graph of count rate after we have drawn them. like we're going to calculate the half-life. And if we find it when it is less than 60, then we are going to extend according to, yeah, that's according to me.
Okay.
Teacher John, I don't know whether it's me or your mic, your voice is not clear on the microphone.
Okay.
It's not clear yet.
I'm not clear.
Maybe you draw closer to your microphone.
Okay, let me try using headsets. I hope
Yes, you're better. It's better there.
You use headsets?
No, the voice has come out now.
Okay, so you can hear me well?
Yes.
Okay, thank you so much. So, like I said, that it is more of interaction. What should I plot against what? We said someone suggested.
It's blurry again. Maybe use headsets.
Okay, how about now?
Better.
Okay, so someone suggested that we plot count rate against the time in days. Of course, count rate is given in per minute. So what is someone is writing on a screen, please forgive us. What should we plot? I mean, what should be our scale, vertical scale? Yes, faster.
According to that chart, people were saying we plot count rate, Vincent is saying count rate against time. Then Amma is saying we plot count rate against time. Count rate on the vertical.
Then time on the horizontal. So I'm asking for the scale. Should we use, first for the vertical scale, should we use 10, 10? What do you think? That every centimeter represents 10 values of count rate?
Yes.
Cyprian?
Yes?
Yeah, we can use 10.
Okay.
This one
okay, this one is a smaller one, it will not fit. Me, I can use maybe 25. If I use 10, 20, 30, 40, 50, 60, that's not going to fit. But of course, for you, as you are plotting, make sure that because you have the entire graph paper, you can use a convenient scale so that you come up with...
in the chart paper saying 20.
20, 40, 60, 80. Okay, let me use 20, 20, 40, 60, 80, 100, 120, 140, and 160. Then horizontal. Horizontal, I can use what?
And the chart paper is still saying 20. Then
okay.
Who gives what says 20? Thaddeus says 25. Vincent, 20.
Okay, 20,
25.
40, 60, 80. Maybe let me clear this. Uh, 60, 80, 100, 120, and so on. If we are to plot 0, 106 on the vertical. Oh, I think I need to check it again. This I'm explaining to someone who was like, why do we have to draw a curve of best fit? And I'm saying that it comes from the equation. If you know, we are trying to relate with the practicals. Most of the graphs that you draw are straight line graphs. Straight line graphs are generated from the fact that if I'm plotting y equals mx plus c, then I expect a straight line graph whose slope is m and intercept is c. Now, if I'm having values that I generate or that I get practically, and these values don't actually give me this straight line, then I think of what we call a line of best fit, a line that best fits the points that I have come up with. Because ideally, a straight line graph must follow the straight line equation given by this. So likewise, this graph does not come from anywhere. It relates to the general equation of radioactivity. The general equation of radioactivity states that the count rate or the activity is equal to negative change in number of particles divided by change in time. The interpretation of the equation is that if you leave a radioactive element to disintegrate, every time that elapses, this radioactive element reduces in number. And the reduction in number is represented by a negative. So if we are to relate this equation to this one up, so they are the same. The standard equation would be y is equal to -1 over x, which when you plot, when you are very accurate, it gives you a curve. Now, we want to relate that because this one gives us a curve y is equal to 1 over x, here we might not be very accurate because the results obtained are experimental results. But after getting them, we now insert that curve that suits the actual equation, because the actual equation is given here. So we draw that curve that is in line with the actual equation. So this is called the curve of best fit. Not necessarily going through each and every point, but balances the points just like we have in the what? Just like we have in plotting straight line equations. Is that okay? Okay, so
it's not straight, may not be okay because there's some 4 hands that are up.
Okay.
Philemon, your hand has been up.
Please decrease. We don't know. Yes, the volume.
My volume is low.
Yes.
Maybe Philemon, you can raise your volume because
I raised it, but
better now.
Are you able to hear me?
Yes.
Okay. Sorry, I actually saw it. It was very low here, and I've increased it. Any other question? Because we want to go to another question.
Good afternoon, Master. My question is, how are you going to be able to draw that line or that curve of best fit? Because after plotting the points, you'll find out that most of them lie in the same line. So how are you going to be able to differentiate?
Okay. Now with this one, the curve of best fit, we don't use a ruler. You just use the free hands. You just use free hands.
Okay.
You get it? You don't have to be so careful that now it must balance so well. No, just the only difference is that when we are drawing a line of best fit, we use a ruler. But here we don't use a ruler, but you can tell that if I draw this line, it is going to go. It might not go through exactly. We might not all get a line that goes through exactly the same points, but you can estimate and say that my graph should come something like that. You use freehands. Is that
Thank
okay?
You, yes.
Now, how do we use this curve to generate or to find half-life? You remember half-life is the time taken for a radioactive element to disintegrate to have its original value. So pay attention to this. To have its original value. If the original value is this, pay attention to this. The original value can be obtained from that table. It was what? Let me call it M naught. It was 162. Originally, it was the original count rate, the very first value of count rate. Was it 162 or?
So maybe you scroll back up, that even for complaining the chat, they didn't get the opportunity to see the question.
Okay.
Okay, they're saying 106.
106. Okay, that's the original. That's the original value. 160. So okay. Those who are writing, do us a favor. So if the original value is 106, 106, then what is the half of that value? Is going to be half of that value is it?
Half of that value in the chat, 53 from Francis. Mary says 53 and Nigeria as well.
Okay, thank you. So the original value was 106. Now its half is 53. Now I come on the horizontal axis and I look for where is 106? 106 was exactly at 0, just when the count rate detector just began. It began when time is equal to 0, and it began with a value 106. So when this element decayed to half the original value, that time was, so it means that you come, draw a horizontal line, then reach our curve, and then find the corresponding value on the horizontal axis to read the time that it takes for this radioactive element to decay to 53. So for those who are using graph paper, you can get that exact value, which I got as 63.02 something, but we can say 63. So that time here is 63. Using a graph, you'll get the actual results. So 63, what does that mean? If I want to get half-life, then I'll simply get 63 minus 0. 63 minus 0, which I get as 63 what? Which I get as 63 days.
So there are 14 hands up, 15. It's signifying that there are many questions to be asked. So
asking.
Yes. And if your question is answered, then you can lower down your hand. Sepriana?
Yes, teacher, my question is,
we
didn't answer the person who asked at first. Isn't the line supposed to be putting all the points? Because like where we were taught, our teacher told us supposed to be passing through all the points.
To pass through all the
points.
Me, I'm talking about a curve of best fit.
Okay. Then next question from Okrut. Please, if your question is answered, you lower your hand. Okrut, Emmanuel, and Hamza.
Thank you very much, sir. Now for me, my question. Is it a must that I'm to draw that line to pass, okay, the line of best fit?
The curve.
I mean, like all the points.
Is it a what?
I think his question is it a must that they should pass through, that the curve of best fit should not pass through all the points?
No, even if it passes through all the points, it's okay.
Okrut, you can type your question in the chat because you're breaking. And then Nielahan from
now let me explain something. Let us get something better. Why I'm saying that, it is okay to have a graph or a curve connecting all points, but the disadvantage with it, let me demonstrate it here. I think I can first stop the sharing, then open the whiteboard here, so that we don't leave anyone behind. Okay. So you were told that a graph must go through all the points. I told you, since it is a machine, anything can happen. From nowhere you have a value, a straight point like that. Now, how are you going to connect? Because in your mind, you are convinced that the line must go through all the points. How are you going to do that? Now, because we can't, by nature of the graphs that I have obtained, it is clear that it is understandable and clear that this was a straight point. Let me see. Okay. The last one I plotted was a straight what? Was a straight point. Is that okay? So in that case, you can't have a line that joins all the points. So that's where now the curve of best fit makes what? Makes meaning. That you just consider a curve that goes through the rest of the points that make a particular pattern. Ignoring this one, of course, now you know that that was a mistake. A right book, please throw those out. A right book, throw that person out, please, so that we have decent work. So, have you seen what I've been drawing? Someone is saying my screen is not visible.
It is on. I don't know, for some people.
It is on, only
it's
that
not clear.
Only that
I'm
someone
trying to enlarge it. So is it back in the center?
Not yet. Okay.
There.
Okay. So, but have you understood my concept of curve of best fit?
People, you just type in the chat if you've understood. Lauren has said no. Joanne, yes. Irona, yes. Okay, I think it's a 50-50. Pardon, no. Yes, 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 yes. Understood. Yes, okay. Yes, teacher, yes. Teacher, there are some few people who have not understood. I think it's half of the class, yes. And then another one is asking how to use the formula.
Okay. Okay, so we go back to our graph. We go back to our screen, yeah? So we come up with a curve of best fit, and I've just explained a curve of best fit guides us in case you have any stray point. So you may not have to draw a curve that goes through each and every point. If you draw it and all the points make a curve, it's well and good. Is that okay? So we found the initial value, and also it's a half. Then we went ahead to find the half-life by determining if the half was if this was the half of the original value, look for its corresponding time, which we got as 53. So the difference between 53 and 0, that is the half-life. 53 and what? 53 and 0. So I think that is okay. Let us first go through. If time allows, we shall come back and have another question that is in line with our calculations. This is specifically graph, but the question is not yet over. We have half-life of was it 53, 63? The half-life is in 63. So, but remember, according to the question, I'm seeing some more hands. According to the question.
So yes, their hands up.
Maybe some
Many
people have not
questions.
Maybe
Many
some people
questions in that topic. Maybe we'll have a seminar of its own for this very topic, because even in the chat there are many complaints. Others are asking for the method. Maybe we'll have a seminar of just basically modern physics to give time to us to understand, because many questions are coming in the chat, whereas some are understanding, others are not.
Yeah, now I get it now, because it is one of the last topics. Maybe some people have not covered the topic, and because we don't have a lot of time, we may not explore each and everything in this limited
Even in the chat, Vincent is saying the reality is most schools haven't taught it.
Okay, yeah, that's a reason. Okay, that's why I'm saying that we can go to another question, because some other questions are familiar. But let us finish it up. Let us finish up the other parts. Otherwise, explaining to someone who did not attend, or where they didn't cover it at all, it might require some more time. Maybe we shall arrange later. But for now, the assumption is that you covered modern physics, and then you are familiar with radioactivity. Is it okay? Okay, so what is the conclusion now? We have the half-life, which is 63. We have the half-life, which is 63. And again, let me take us through the conclusion that I got. The calculated half-life of radioactive material from the graph is that, which is equal to 63.02 minus 0, which is that. So since scientists recommended that the environment will be safe when the half-life value is less than 60, was it in the question?
Chapipa is saying that it was 53, not 63.
The half-life?
Yes.
No, it was 63. If you plot, you'll get 63. 53 was for this one. Don't confuse. This one The 53 is on the vertical axis. Then the first one is on the horizontal axis. So the value here is 63.02. Then the value on the vertical axis is the one that is 53. Because when we are plotting, we have x and what? And y. So the x, which is time, is 63.02. This value. Is that okay? Remember, my scale is big, 50, 100. Where you see 50, you see it as if it is very near to 50 and you think it is 53. No, it is 63. Is it okay?
Then you type in the chat if you have understood.
Okay. The question was asking that, the question was like, where is number 3? There was a condition. The scientists recommended that the environment will be safe for use again when the obtained half-life is less than 60. Now, our half-life has been 63. What do you think is going to be the conclusion? Can someone tell us?
Okay, so if your hand is up, you're going to give an answer. Shall raise the hands later on. Imran, okay, Matia Mulumba.
Mm-hmm.
Not safe, so.
In the chat, let me just read from the chat. In the chat, same way, Joshua is saying the environment isn't safe because the half-life is above 60. Then Phoenix is saying, someone using if it is saying not safe, not yet safe, it's not yet safe. Yes. Anyone to give a proper conclusion? Hamza? Hamza, unmute. Sorry, unmute again.
It is not safe to be used because the half-life is greater than 60.
So we have the response here. Since the scientists recommended that the environment will be safe when the half-life is less than 60, it appears the current radioactive material does not meet this safety criterion or condition. Therefore, residents should follow the advice to relocate for their safety. Is that okay? So the question required us to find the half-life and then draw a conclusion. Then part B, sensitizing people about risks associated with the radioactive materials. So these risks are categorized into health hazards and environmental what? Environmental effects or impacts. So the health hazards, short-term exposure. With the short-term exposure to these radioactive radiations, maybe just a reminder, what are the radioactive radiations that we talk about? Gamma ray. Yes.
Okay, in the chat. Let's hear from Chivuka SS, examples. Okay, Elvis, examples of radiations.
Alpha radiations and beta radiations.
Okay. So
in the chat, there are X-rays. X-rays, gamma, alpha, and beta.
So we have alpha particles, beta particles, and gamma rays. They are 3. alpha particles, beta particles, and gamma radiations. Is that okay? So alpha, beta, gamma. So the effect of exposure can lead to acute we have when it is short-term exposure to this kind of radiations, they cause skin burn, vomiting, and so on. For the long-term exposure, increase the risk of cancer, genetic mutation, and cardiovascular diseases. So genetic mutations, for those who are follow of documentaries, you remember the story of Nagasaki and Hiroshima, that bomb explosion. Up to now, I think it's coming to 100 years. They are still producing children with disabilities. So because of that atomic bomb that was thrown in those two cities, the impact was so big that it can create genetic mutation that goes through generations and generations. So yeah, it can also cause cancer because these radiations kill the live cells of the body. Is that okay? When exposed to high doses, it can even lead to death. When I say can be fatal, that means for very high doses, it can lead to death. Is that okay? Okay, by these ones, you can simply read. We have them in chemistry, I think, as well. So environmental impact, contamination of soil and water bodies. Here, you know that when these radiations are exposed to the environment, they are absorbed by the soil and the plants. And when they're absorbed by the plants that we eat contain these radioactive materials. So on this note, that's why we discourage people from eating yams from Bwaise. Have you ever heard of Bwaise yams? So they seem to be sweet, but they are contaminated with a lot of radioactive elements and radioactive materials. Those are hard metals.
Shall people you're talking to have never heard of it? Most of them. See, it bad.
Okay.
Maybe they don't stay in Boise.
Okay, but
they don't stay around Boise.
My point is, when these radioactive materials are absorbed in the soil, and then you plant food in that soil, this whatever you have planted absorbs those radioactive materials, and at the end of that day, when you consume that food, you consume the radioactive elements with it, and that's how it becomes very, very, very bad. Also, it can go into water bodies when you drink that water. And these are hard metals that are very difficult to dissolve, meaning that even if you boil, you may not get rid of them. Is it okay? Okay, flora and fauna, that is the ecological imbalance. What's the meaning of flora and fauna?
Okay, flora, let me see. Flora, okay, let me answer. Flora is basically plants, then animals are fauna.
So, but maybe to add on that one, it is like where you find a group of species of animals, or a group of species. I don't know if even plants are termed into species, but where we have exposure to radiations, it can make the whole species extinct. For example, where we know that Gorillas are found mostly where? There is that specific regions where we have only gorillas, not so? So, where we have now these radioactive elements, in a way, they can affect the presence of those animals, maybe affecting their lives, and at the end of that day, they become extinct, meaning that they cease to exist, or there is imbalance where you find you used to have one region is more of these animals, another region is more of these animals, that kind of balance. So you find that in the whole country that there is a certain species that has been lost completely, because in a way that species was affected by the radioactive elements. Now these radioactive elements, maybe to add on, they are not things that you see. Most of them are mild, mild, meaning that most of them are not direct. They don't come with that full force, and effects are so much visible. So you can realize that some of these ones we expose ourselves to, the effect is gradual. It takes some time, but it takes effect in your body. Is that okay? So people who are near those factories, so you find that the effect might not be instant, but after some time, someone starts developing different kind of diseases, different kind of disabilities after some time. Sometimes it might not be that very person, it can come through his or her offspring. Okay, these ones we shall read. I will share the soft copy. Handling. So here we are guided on how to handle radioactive materials. So how to minimize or prevent exposure to radioactive materials. So and their effects. So we are saying that minimize or limit the time spent near radioactive materials. So people who work in factories, specifically in radioactive laboratories, they are advised to spend a very minimal time in those environments, and also maintain a safe distance from radiation sources. Use shielding materials like a lead or concrete or block what? To block radiation. So we know that among the three types of radiations, the alpha, beta, gamma rays are strongest, not so? So whereas alpha particles can be stopped by a sheet of paper, beta particles can be stopped by what? Yes?
Okay, if your hand is up, you're going to answer this question. Teddy? Teddy, unmute. Okay. I can't hear Teddy. Mercy Bahati?
I think thick aluminium.
Thick aluminium. So
as I say, a thin sheet of aluminium. Edra. Yes.
Okay. Oh, this is a sheet of paper. This is a sheet of aluminium.
So someone says wood and tin.
Wood.
Mm.
Okay. So my point here is that what do you expect at point A? Of course, we are having all the radiations, alpha, beta, and what? Alpha, beta, and gamma. So at B, what remains?
Vincent? Vincent, unmute. Sepriana.
At B, we expect the gamma and beta particles to be there.
Gamma and beta, that means that alpha particles have remained at F. Then at C,
yep, we only expect the gamma rays.
Gamma. So meaning that to be very safe, use the lead, because the lead can protect against all the three. Is that okay? Okay, another one, the PPE, the personal protective equipment. And that one, we have the gloves, the masks, and so on. Some of these ones are mentioned in the laboratories, but people don't take them very serious. By the way, for your information, even these laboratories of ours, there are some radioactive elements, only that we can't see them and we take them for granted. That's why it is advisable that when you are operating in a lab, whether you're a student or a teacher or anyone, please ensure that you have these PPE, the personal protective equipment. Is that okay? And also radioactive detectors. Can someone tell us what are the radioactive detectors? Examples.
Raise your hand if you have anything to add on. Okay, Trevor Albert. Trevor, unmute.
Yeah. One of them is a gigamolar tube.
Gigamolar tube. Another one.
And photographic film. Yeah, that's all I heard.
Okay.
In the chat, Joanne says cloud chamber. Then Wafula says film discs darken when exposed to. Then Shadrach says scintillation tube. Yes, that is what is in the chat.
Yes.
Then
yeah,
ionization chambers from Hamza.
All those ones are true. The most common ones are gigamolar tube, ionization chamber, and photographic film. So at school, at least you advise in your capacity, there should be at least one, because we can't see these radiations with our eyes, yet they have a side effect on our lives. So there has to be at least one to detect. In case they are there, then they are experts who can come and do the needful. So proper disposal, follow government regulations for the disposal of radioactive elements. So you don't simply come with your hands and then you think of picking them and throw them away. There are guidelines. In Uganda, we have, I think it is called Atomic Energy Center. Atomic Energy Center that deals with that is directly in charge of this kind of studies, the radiations, and it is in line with atomic contents. So there is that organ. So when you realize that maybe you are using a radiation detector, and you find that it is counting, it detects some radiations, you don't have to panic so much. You just have to know that there is an organ or an agency in a country that can guide for us as far as that is concerned. Is that okay? And also use designated containers and storages. Of course, there are those designated containers and storage facilities. Sorry. So we also have emergency preparedness. What are you supposed to do? Beware of emergency procedure in case of radiation. Have evacuation plan in place. Okay, this one is already through in Uganda specifically. We have them in theory, but practically it is very possible that in any organization, all these emergency emergency plans are set in place, just like we have emergency plans for fire outbreak. You know that when fire starts, there is a plan, and that plan has to be known to each and everyone, so that in case it happens, you know what to do. So even this one, it's an education where we expect everyone has to know what to do in case a community is radioactive. Is that okay? And now, as a country, we are entering into the era of producing, and not producing, but mining uranium. I think it has already started, but making proper use of uranium. The moment you hear about that element called uranium, then just know that we are now in atomic energy. And atomic energy is not only for the bad cause, like people relate it with atomic bombs. It can be used to generate electricity. But remember, I told you uranium as an element is a radioactive element, which if not properly handled, it can cause all those side effects we have talked about. And in Uganda, like I've told you, study shows that they cited uranium somewhere. I'm not very sure, but I think they started also on the process of generating electricity using atomic energy, and specifically making use of uranium. So we are not far away from these radiations, only that you can't see them with your eyes. So we have to always be on the standby. Is that okay? So the other question was an element X of radio. This one, I think we can work it out together. We're still on number 3. Those people who are writing in our screen, you are eating a lot of our time. Help people to understand the value of the number of neutrons of a nuclide Y formed. So Y is formed after when X mass number 208 and atomic number 104 disintegrates. So we don't know the mass number, we don't know atomic number, but we know that it emits 3 alpha particles. By the way, an alpha particle is the same as a helium nucleus. And helium is given as 4 and 2. So you can take note of that. An alpha particle is the same as a helium nucleus. So instead of writing alpha, I can replace it with the symbol for helium. So 3 alpha particles and 4 beta. What is a beta particle? A beta particle is an electron. A beta particle is an electron. You can take note of that also. So 4 beta particle plus gamma rays. Gamma rays carry no charge. So we don't put anything. They are not charged. So let me rewrite my equation as 208, 104. Someone kindly, you remove this person who is putting green ticks. You remove that part. It's the same as a helium nucleus. And you know, helium is given as that one. It has mass number 4 and atomic number 2. A beta particle is also the same as an electron. An electron has mass number 0 and it carries a negative charge. And it carries a negative what? Carries a negative charge. Is that okay? So we substitute. This is going to be 208, 104 X. After disintegration. By the way, for those who have learned modern physics, you know that in a language the language that we use Ajiri. Please remove Ajiri. The language that we use is that when one element disintegrates by emission of radiations to form another element, the element formed is called the daughter nuclide. Okay. Who is this one now? Please just know that these videos are recorded and they are uploaded on YouTube. So don't express your hooliganism.
Some people, if you keep on doing that, we can see your names. So you will be ashaming your own self. So once you do it again, you're going to be removed for good. Permanent removal. You will join back and it will be impossible to come back. Let's be grown. We are nearing to 11. We don't need to have such things waste our time. You can also see the time and we are still on item 1.
Okay, so we say that this y plus 3 alpha particle, alpha is represented as 4 and 2. Beta is represented as 0, -1. Then the gamma rays. The gamma rays. So let me just call, because I don't know the mass number and atomic number of y, I just call this one A, I just call this one B. So to balance the equation, I can equate all on the left-hand side, the mass number, equate it to the right-hand side, the corresponding values of the mass number, which is A plus, so here we shall multiply, 3 multiplies both 4 and 2. If I'm dealing with the mass number, I'll multiply 3 times 4, which I get as 12 plus 4 times 0, I get 0. So A becomes 196. Then we do the same on the horizontal. 104 is equal to B plus, now here 3 multiplies with a 2, which is a 6, and 4 multiplies with a -1, which is a -4. So 104 equals B plus a 2, and our B becomes 102. So the 196 represents the mass number of element Y, whereas 102 represents the atomic number of element Y. So the difference between the mass number and atomic number is the number of neutrons of that element. That okay? Number of neutrons of that element. So just subtract 196 minus 102. Okay, I think we can go to another item. That okay?
In the chat is saying she has understood. Say this is understood. So just in case, okay, people are saying they've understood. Let's at least understand that bit, the part for half-life, and the formula will be prepared for a special session. So I beg we at least get that from this particular scenario. Okay, teacher.
Okay, so now that some people have not covered modern physics, I also wanted to take us through digital electronics. What is your say? Have people gone as far as digital electronics? We look at something?
People just type in the chat, we see feedback. I think teacher, let us do topics that we have not done. Sorry,
Okay.
that we have already covered so that people are able to, so that it does not become a teaching session as far as time is concerned.
Okay, so this number 4.
Adoko, it's okay, take us to the teacher. HK says no. My school has not yet. That's from Ruth Colette. We haven't covered. Haven't covered. It's better we learn it here. Okay? No.
Okay, if there is another meeting, I think we shall go.
Yes. So I think we can go through it.
Now.
There are very few people who have not done it. I think they can pick it up. Someone here, firstly, is saying digital electronics is simple.
Should we go through digital electronics?
Yes, we can go through it. Yes.
Okay, but since I'll first give a very brief recap. So my prayer is that even if we get the number on modern physics and this digital electronics better, it would be good. I will leave behind the solutions and the questions so that anytime you can inbox me and I guide where need be. Is that okay? Okay. Now, let me see. Okay, we are going through digital electronics like people have requested, yeah? Are you able to see my screen now?
Yes, teacher.
Okay. So you should have heard of some conditions where you only have two solutions, where you have only two ways. You don't have any other. You have either to say no or yes. It is either high, you are either high or low. You are either sleeping or awake. You are either, what else? Laughing or sad. Have you ever heard of such cases where you are only left with two options? Someone suggest any other case. Yes? Suggest any other case where you have only two options.
If I've asked you to unmute, excuse me? First introduce yourself.
The option of saying you are either alive or dead.
It is either life or death. Something can either be true or false. There's nothing like a partial truth.
Shakira, Dr. Hills, you rename yourself. Next time you won't be picked for contribution. Shakira.
Okay. One last
in that chat, choose. You are either happy or sad.
You are either happy or sad. So now all these conditions make up what we are going to look at. It looks to be somehow abstract, but when we learn it, you realize that it is the simplest topic. So the simplest that we can think of is a switch. We all know a switch. When you switch on, it is either the switch is either on or it is off, not so? The switch is either on or it is off. So it can't simply be midway. And now a switch acts as an entrance to any circuit. You know, when we are drawing our circuits, what happens? Do you realize in practicals that when you draw a circuit, maybe there is a bulb, there is a battery, we always put a switch somewhere. Why? Now, a switch acts as a gate. It allows current to flow or not. Allows current to flow when it is closed. Allows current not to flow when it is open. You see there are two options. You get it? And why are we calling a switch a gate? Can we relate to the gate of the school? What do you think a gate of the school does? Give me some 5 reasons as to why there has to be a school gate. Yes?
First of all, privacy. Second of all, to let students in and close the gate when people are late. Another one, to let parents in.
Okay.
The fourth one, yeah.
To add on Imran's answer.
Okay, so to allow parents in for privacy, security, and so on. Now, a switch in a circuit or in a digital circuit plays all those roles. So it allows current to flow. It gives permission, or it is a decision making whether current will flow or not. And that's why a switch is called a very simplest gate in line with electrical circuits. It's also a gate because it can close, it can open, just like a car has the right to close and to open. When it closes, it means no entrance. When it opens, it means you are free to enter. So when we talk about digital electronics and specifically logic gates, we simply mean something that can have only 2 options, yes or no. It's logic in a way, because with just 2 options, there are millions of tasks that this can do. There are millions of tasks that this can do. And you all know that a computer is designed to have only 2 options. That is a 0 and a 1. But with only those 2 options, it can do millions of tasks, like you know. But with just 2 options, it is either a 0 or a 1. Whereas our counting system, it is in what? It is in base 10. Base 10 is where we count from 0, 1, 2, 3 up to 10. But a computer's counting system is a binary base. If it is not 0, it is a 1. But with only 2 options, it can do very many tasks. Is that okay? So that's where now the logic comes in. So a gate, we know that a switch we are talking about is a physical switch, the one that you use with your hands, but they are also switches that are inbuilt within the motherboard, switches that are in the computer. Those switches are called, who knows the name of those switches? Those automatic switches, the one that we can't, it is already inbuilt. Yes?
Francis seems to have an answer.
What is the name of those switches that are used on electrical circuits or motherboards?
Okay,
Yes,
let's hear from Karen.
Yes?
Karen has failed to unmute.
Okay, they are transistors. They are transistors. So a transistor is a switch. The only difference between a transistor and these physical switches, you know, these physical switches, if you switch on and off very fast, higher chances are that a bulb will blow. Do we understand that? Number two, there are more chances that in a second you may not make 100. You may not make 100 turns in switching on and off, on and off, on and off using your hand. You can't make 100 in just 1 second. And yet the digital circuits are designed to operate that a switch can interchange, go on and off million times in one what? In 1 second. So it was realized that because this physical switch cannot do that, it can't go on and off million times in 1 second, they discovered transistors which can do that. Is that okay? So transistors can switch on automatically very many times at a very high frequency. So they are called gates. Is that okay? Because they allow the current to flow or not to flow. Is that okay?
Brian seems to have a question. Brian, please unmute.
And for me, I was just asking, like, is the thermostat also a switch?
Thermostat, it can also act as a switch because it is a variable resistor. It's not exact switch, but you know, when its temperature varies, if it is connected to something that is temperature dependent and its temperature rises, there is change in resistance. So if a system or a circuit is designed that when resistance changes or when resistance increase, light will go off. When resistance reduce, light will go on. So if you use a thermistor, which can practically do that, it can increase and decrease resistance. It means you can see a bulb going on and off automatically, even without any switch, because this connected to the bulb, the thermistor, for as long as there is change in temperature, then it means there is going to be variation in the current. So in that way, the thermistor can also act as a switch. Is that okay? Okay, so we don't have a lot of time, yet I want us to have a very brief introduction, then we shall try out one number. Is that okay? Now, let me consider my bulb. Let me consider this one as a switch, and then I have my bulb. Someone is going to tell me. Remember what I told you that in a computer works in binary base. It is either a 0 or a 1. Now we have said that where we have two options, it is either on or off. It is either high or low. It is either true or false, and so on and so forth. So it is either a 1, if not a 1, it is a 0. If it is either a 0 or a 1. But now this one happens on condition like we are going to see. For example, if I have my bulb here, and then I have my switch. So if the switch is on, we have a condition when the switch is on and when the switch is off. Let 1 represent on and let 0 represent off. Is that okay? Are we following? Let 1 represent on and let 0 represent off. Let me draw it again here.
We are with you.
Let 1 represent on and 0 represent off. So supposing that I close the switch. When I close the switch, that is current is going to flow. That is an on. Is that okay?
Yes.
When I open the switch, current stops, the bulb stops lighting. That is an off. Off is represented by a 0. Is that okay? So meaning that a digital, this digital sensor, for it may not see the word on or off. The moment it reads 0, it will know that the circuit is off. I mean the switch is off. When it reads the 1, it will know that the circuit is on. Is that okay?
Yes.
Okay. Now, supposing we have two, let's assume we have two switches now. Connected to a bulb, a battery. Okay, this is a battery V. Call this one switch K1. Call this one switch K2. I say K1. I say K2. And then here I have my result. So let me say K1 is open, and then K2 open. These are the different possibilities. K1 can be open, and then K2 closed. K1 can be closed and K2, and then K1 can be and K2
open.
Open. Thank you so much for responding. I get encouraged also. Now what happens when K1 is open and K2 is open? These are simple circuits that you have always been looking at. We are looking at a switch as a gate, and a gate allows something to go through. So when K1 is open,
the current will flow.
No, there will be no current flow.
When both are open, current will not flow, not so?
Yes.
Yes.
So when both are open, current will be off. Is that okay?
Yes.
How about if K1 is open and K2 is closed?
No current will flow.
Current won't flow because the circuit won't be complete.
Very good. The circuit is also how about when both are closed?
On. Current will flow.
Yes, it will flow.
No, it won't.
It will.
Will. Because there will be a complete.
If they are both closed.
Circuit will be complete.
Yes.
Hello?
Hello? Can you hear me?
Yes, we can.
How about when K1 is open and K2 open? When K1 is closed and K2 open, what is going to happen to the current?
Current will flow.
Not flow, sir. It will not flow.
Current
will not flow.
Current will not flow, not so?
So it only flows when both switches are closed.
It will flow.
It only flows
Because
when
if
both
K1 is
switches are
closed, K2 is open,
Current will
will not flow because the circuit is not completed.
Okay. Now remember in digital electronics, we are dealing with only two conditions. It's either on or off. It is either 0 or a 1. We said this off represents a 0, on represents a 1. So in terms of binary digits, when I talk about binary digits, I mean 0, 1. So the off is going to be a 0, a 0, a 1, and a what? A 1 and a 0. So the circuit.
Sir, I have a question.
Yes.
Sir, I'm trying to fire the second switch.
Yes.
Yeah, is it a two-way? Because we need also just to know that it's a two-way.
Is it a what?
And because is it a two-way? One gang two-way.
Teacher.
Yes.
Teacher?
Yes.
Sir, why did the current flow when all switches were closed?
When all switches are closed,
The circuit is complete.
the circuit is complete.
If the
When
circuit
both
is
switches are closed, the circuit is complete.
okay, I get you now.
But when one of them is open, it means current cannot flow.
Now, teacher, which type of gate is that?
So we are going to reach there. I don't know. Now we are left with the 2 minutes, but I wanted us to understand. Now, have we understood this table?
Yes,
How we
please.
Yes,
We
teacher, we've
understand.
got it.
Yes, sir.
The
Ask the question.
Yes.
Teacher, I can understand it. There is a lot of disorganization.
In what?
That
Okay.
I think you guys have to first mute it.
Must meet the guys.
Admin, can you meet other people, please?
So, we have the bulb. We have our circuit like this, yeah? This is a battery. This is our K1.
I think Teacher John has got some network issue. Hey. Uh, Yes, so he has got some network issues. Okay, so okay, I'm going to find out what's really happening. But what is really very important, you need to understand those gates, and you must. Yes, I'm trying to see whether I can get him back. Yes, I don't know who's this one sharing. Okay, let's just be patient for some few minutes, and then we see whether. Okay, he's back. He's back. Yes. John, go on.
Yes. Okay, ladies and gentlemen, let us finalize with what we are looking at. Okay, so I say that if we have a tree, this is a battery, K1, K2, we said a switch acts as a simplistic gate. Look at that. If I draw my truth table, generate a name from the fact that we said as far as digital electronics is concerned, it is either true or false. Is it okay? 0 or 1. That one we discussed. So we're still looking at happens if K2 is open and K1 is also open. K2 is open and K1 is closed. K2 is closed and K1 is open. K2 is closed and K1 is what? K1 is closed. So the result is going to be, now this is a simple circuit that you have already been doing in the but if I open current is going to be off, not so. When I open one and I close the other, here it is going to be.
Mr. John. Mr. John?
Yes, Mr.
Yes, I don't know that you are just a bit far away from the microphone. Like,
I'm not audible.
Now you are clear.
Okay.
You are
but
clear.
we have gotten a challenge of these people who write in.
Now, what we do, Mr. John,
yes,
go up there on your screen, and then there is somewhere where those Zoom details are. Then there are some 3 dots there.
Yes.
And disable annotation for others.
Oh, okay. I wish I knew it at the beginning. They have disturbed us throughout. Okay, and they have disorganized our presentation. Nevertheless, we can continue. So we are saying that if K2 is closed and K1 open, what happens? Current is going to be off, but when both are closed, then current is going to be on. So, but remember, I told you that in digital electronics, the off is represented by a 0, 0, 0, and a 1. Is that okay? Now, is that okay? Let us relate it with something. Let us relate it with something because we know the types of gates, logic gates are the AND, the OR, the NOR, and so on. But before we let's have another parallel combination. People write down this one because there's a concept I want us to leave after we have understood at least that part. So I hope you have taken note of that. How about if these switches were arranged in parallel? What would happen? This is our battery. So this is K1. This is K2, and then we have this one I told you we call it table. So I have K1, K2, and then the result. This result tells us whether bulb will light or no. Then we shall find it out using that. So we have switch one open, and this one also open. When this one is open, and this one closed. When this one is closed, and then this one is open. When they are both closed. So I want to have a few, maybe one person, to share with us what is going to be the result. What happens when both switches are open? Bear in mind the result will go before in the series arrangement. When both are open, what happens?
Nicole, unmute. Okay. Nicole,
Teacher,
go
is
on.
not true.
Nicole, are you giving the answer?
No.
Okay. Elika?
Okay. When both of the switches are open, no current will flow, so the bulb won't light.
It will be off.
Okay. Then when switch K1 is open, then K2 is closed, the current will flow through that upper side. Then then the bulb will light. Then when K1 is closed, and then now K2 is open, current will flow through the downer side. Then as well the bulb will light. Then lastly, when all the switches are closed, current as well will flow. Then the bulb will light also.
Okay, so this one is going to be a 0 in binary. 0, 1, 1, not so. So how do we interpret this? We interpret it in a way that the bulb will light. The bulb will light either when K1 is open, or when K1 is closed, or when K1 is what? Is closed, or when both are what? When both are closed. You take that? Should I repeat? So here we say that the bulb will light only if K1 is open, K1 is closed, or only K2 is closed, or both are closed. And that is how we come up with the OR gate. Is that okay? That's how we come up with the OR. That's how we come up with the OR. So the OR gate provision, that for as long as there is one switch that is closed, current will still flow. Is that okay? Current will still flow. And we are going to say that. Then on the other side, On the other side of the series arrangement, you remember what we came up with? K1, K2, and then the result. So here, the bulb can only light if and only if both K1 and K2 are closed. K1 underline the word and. Both K1 and K2 are closed. So it must be that both K1 and K2 are closed that the bulb will light. So the series arrangement gives us what we call the AND gate. The AND what? The AND gate. Is that okay? So the simple interpretation is that if K1 is open, that's a 0. K2 is open, that's a 0. And it means that we shall get 0 because the bulb will be off. So when K1 is open and K2 is closed, still I get a 0. The same can be obtained by simply multiplying 0 times 0, you get a 0. 0 times 1, you get a 0. We are dealing with the AND gate. And also, when K1 is closed and K2 is open, still the bulb will not light. I get a 0. Can also be obtained by when you multiply 1 times 0, you get but when both are closed, when K1 is closed and K2 is closed, then the bulb will light. Which result can be obtained when you multiply 1 times 1, you get 1. So this result is a result that corresponds to the AND gate. The symbol for AND gate is that where if you have 2 inputs, then the output would be as follows in the truth table. Is that okay? Is that okay, friends? So that is the origin of the AND gate. Then we look at the origin of OR gate and we are, I think that combining this, the AND and the OR, maybe we can combining that. So let us go to the OR gate. This is the AND. The OR gate, so that it deals with parallel. Deals with parallel arrangement. This is K1, K2, and this is our key. So the OR gate says that this is K1 and K2. We can get the bulb lighting either K1 closed or K2 closed or both of them are closed. Still you can get the one. So when K1 is closed, K1 the bulb will light. That's the one. When K1 is closed and K2 is closed, the bulb will light. That's the one. When K1 is open and K2 is closed, the bulb will light. And when both are open, is that okay? So this is that is the O, the gate. O is capital O, capital R. So the same result can be obtained by simply adding 1 plus 0, you get a 1. 1 plus 1, you get 1. You don't get it 2 because we are dealing in binary system. Binary, when you add 1 and 1, you get a 1. 0 plus 1, still you get a 1. You only get a 0 when you add 0 plus 0. So this one is the OR gate. So I'll say the simplest demonstration of the OR gate is the parallel arrangement. And then the simplest demonstration of the AND gate is the everything arrangement. Of course, we have daily life applications, but we can see them another. And then lastly, we can look at the node. The node inverts the input. The node is the symbol where if the input is 1, for it to simply invert the input to the opposite. If the input is 0, then the node gets converted into a 1. That is that okay? Altogether, I think I can stop here for now. We shall have applications, practical applications. Unless if Mr. Kaziba would like me to continue, I can continue. Mr. Kaziba.
Not really, because I'm seeing, looking in the chat, I think their data bundle is getting used up. Yeah.
Okay, but like I said in the beginning, I have notes for the slides. I can share the slides in our group. I can also share the actual notes of these ones so they can read. I'm also going to share the questions, the questions we were discussing here, as well as their solutions. So, any question?
Saying the hands up, but let me first lower them. Those who are putting up your hands, let us just have people who have questions to ask. Let me first, you first way to put up the hand, because I know. Now, in case you have a question, raise up your hand and ask. Okay. Queen. Queen, ask. Okay, Queen is fading. Yes, Queen.
I'm asking, I just want to know the last gate. What is it? Its name. Turn of A and negative A.
The one of the node. So we have the and we have the O. So these are the three basic gates. And we said gates are simply building blocks of digital circuits. So the node, the AND we have looked at it, simply example that we have seen is the was it the series arrangement? Yes, the series arrangement. Then the O, the simplest example we have seen is the parallel arrangement of switches, if we consider switches as gates. The node simply inverts the input. If the input is a 1, it gives 0 as the output. If the input is 0, it gives 1 as the output. They are applications, but we shall see them later. Then, when we combine the node and the AND, we come up with another one. Its name is NAND. So it's very simple, but it's another time. If we connect the node and the OR, we come up with the NOR. So there are also other things. The AND, the NOR, and there are some others I'll see another time. Is that okay? But today I wanted us to know at least the first, at least this. But majorly the AND and the OR. The applications lie, for example, if I want to set an alarm in my home, I can put conditions that the bulb will light if an intruder gets in. So that's a condition. And there is also another condition. If he gets in and maybe makes a sound, that's when the light or the alarm can switch on. So these conditions, we shall see them another time. But this can be applied in daily life. Yes, another question?
Wait, first keep on. Yes, Alvin?
Yes, my question is about how potential dividers operate normally.
Oh, we have not reached to potential dividers. I hope that will be for another time. We have not looked at potential dividers, the actual working of these volume increasing knobs. That is a data application of potential divider. But we shall see them. They are very simple.
Yes. Okay, thank you very much.
Yes, any other?
Safra, unmute.
Good afternoon, sir. Sir, I'm requesting that maybe if you have those notes, you post them on the group, because some of us have not got what you were talking about at the last minutes, because your volume was too low. We are just requesting for that last bit.
Okay, I'm going to share the notes.
Thank you, sir.
Francis?
Yes, teacher, I've understood all the okay, I've learned about the two gates, the one of and or, but then the last one of notes. Could you please elaborate? Because I didn't understand anything on it.
Okay. Can we go through it? Or we shall begin with it another time.
We shall begin with it.
Okay.
But this one is simply the opposite. That where you have the input as a one or the on, it inverts that input and gives the output as the opposite of that one. So it's just that if you have a one as the input, then the output you expect a zero. That's why it is called the NOT. We shall see how it works practically in daily life. We shall have some questions. Yes, any other question?
11.
Thank you, sir. So in case they have given you an item concerning digital electronics, and then they tell you to design the system, do we construct the number of possibilities, or we draw the other diagram having the symbols?
Hey. It depends on what the question is asking or what the question requires. The question can guide. So sometimes a question can simply ask you to draw a truth table. They can ask you to, now I've not talked about also the Boolean algebra, the kind of simple mathematics we have been looking at. That 1 + 1, you get a 1. This is a Boolean, someone who's called Bully, something like that, but he's there in the notes. So that is called the Boolean algebra. Because someone would ask, how about, why is it that a 1 + 1 we get a 1? It's not in the usual mathematics that 1 + 1 you get a 2. Yeah, we get 1. So a question can be specific that indicate the Boolean equations or the logic gates and symbols and the truth table. Normally, there are very few questions that come with these kind of questions. They are not so much complicated.
Okay, so can I get the possibilities without constructing the logic gate?
Without
constructing the logic gate?
Yeah, you can.
Okay.
Thank you, sir.
But in most cases, a truth table is inevitable.
Okay.
That's dismissed.
But maybe I can also add something. There is combination, like we talked about the NOR, the NAND, the X. There are other kind of logic gates that we come up with, that these guide you to come up with a truth table. So there is a combination where you combine one gate and another to know the result. So it is from that arrangement that you come up with a truth table. So in that case, then the diagrams are inevitable. Yes?
Okay. There is hope. Hope. Okay. Hope is not unmuting. Tyran. Aporin. Hope, go on.
Yes, teacher.
I think Hope is not talking. Hope, we are not getting you. MG.
So just asking the timetable.
There is some.
You're asking for?
Something that was sent in the chat.
Yes.
I was just asking for tomorrow's timetable.
Okay, tomorrow it is parents meeting. Parents are going to learn something tomorrow. Okay. The link, those who want the link, it is in the chat. Okay. I think Teacher John, I think because there are other questions, but they are failing. So we shall get time next week. We shall get time next week, and then we shall maybe continue and help them out. Yeah, but
Maybe.
allow first, thank you so much for the great session. Maybe in case you can first complete what you really want. It is fine.
Yeah, just to leave you people with this one, the potential divider. Like I said, it is a simple one, but something beneath it. So if this is my R1, R2, these are just resistors connected in series. Resistors connected in series, and then current is going through to R1 and R and R2. So if I'm tasked to find a voltage across one of the resistors, then I use a formula. This one is called the potential divider formula. So it relates to the voltage. This is supposed to be V out. Sorry. This is V in. So it relates the input voltage with the output voltage. Output voltage is the voltage across the resistor that you want to get. So if I want the voltage across a 2 ohm resistor, then the formula is I get the input voltage times the R2 out of the sum of R1 and R2. This can be derived, but for your case, it's simple. You can have it on your finger. So similarly, if I'm interested in maybe the voltage across R1, then this the one I term as V out. If I want to V out across R1, what is it going to be? V in times and tell us. Across R1, we just say is V in times a fraction of resistance. Now this one becomes R1, we begin with R1 out of R1 plus R2. It is a simple formula. You just substitute. If the values are given, you just substitute. If this is 1 ohm and maybe this is 2 ohm, the input voltage is voltage. Here I can get the V out as 6 times 1 out of 1 plus 2 is 3, which I get as 2 volts. So here I can conclude that the voltage across 2 ohm resistor is 2 volts. So that means automatically the voltage across 1 ohm resistor is 4, because they are series. 4 plus 2, you get a 6. So in other words, the potential divider gives a fraction of voltage across any of the 2 resistors, any of the resistors that are arranged in series. And we said such application arrangement is applied where we, for example, on radios, those volume increasing knobs, they apply this kind of arrangement. Yes. So that's the potential divider formula. I think next time we meet, we shall have more application and the combination of the logic gates we have not looked at. What happens when they are combined, and also some questions on potential divider. Yes.
Okay. I think, dear students, we may not be able to go beyond this, but good enough. We shall link up. Teacher John is still with us. We shall be able to meet and then see what we can do. Otherwise, we want to thank you so much for joining this session. We have a few days to go for our UNEB papers. Kindly sacrifice as much as you can, such that at least you go out when you are happy. Teacher John, we want to thank you so much for the sacrifice, but for sacrificing your time to be here with us to teach us. We are really very grateful. Thank you so much. And we are praying that may the good Lord bless you abundantly in everything that you are doing. Dear students, we shall meet again on Monday for another session. But for the other morning session, I'm still thinking about it. I will let you know before today ends. Yeah. Thank you so much. Me wants to lead us in a word of prayer. May you can lead us. Me? Okay. I think, yes. Oh, sorry. Me, go on.
Let us humble ourselves and we pray. Lord God, we thank you for helping us finalize our discussion. We hope to do the best come UNEB 2024. Thank you.
Thank you and bye everyone.